this lesson focuses on state machine design. So what is a state machine? A state machine is a synchronous sequential circuit consisting of a sequential logic section and a combinational logic section, whose outputs and internal flip-flops progress through a predictable sequence of states in response to a clock and other input signals. In other words, a state machine uses a combination of combinational and sequential logic to make decisions on outputs based upon the inputs it's given. A state machine will hold a state until new inputs are given. It kind of looks like this. We start with our inputs, and then the inputs go into combinational logic, which are then held in memory, which are controlled by flip-flops. As the clock signals come in, it then allows the flip-flops to send the signals to the outputs for into the combinational logic, and then our final outputs. As you can see, we do have some items that come from the memory back into the inputs. Okay, so what are the parts of a state machine? Well, we have the input combinational logic, the memory, which is in the center, and then the output combinational logic. And this is exactly what we just saw on the last slide. So again, we kind of make a sandwich with the combinational logic to the memory, which is sequential logic, using flip-flops in the center. And again, that's all controlled by a clock signal. So what is this memory that we keep mentioning? Flip-flops determine the number of states in the design and trigger the state transitions based upon the inputs. Now, when we talk about a state, that means the value that we're trying to have in that moment. And then in the design, we have to trigger the state to move from one state to another. So, again, that block diagram, we have the inputs that come in, and the flip-flops are really what control this to make sure that we have the correct output at the end of the block. So, where would we see a state machine in real life? Well, many everyday devices are actually controlled by state machines, including traffic lights, garage door numeric keypads, as well as vending machines. So how do we create a state machine? Well, first we have to create something called a state graph, and we're going to take a closer look at what a state graph is in a little bit. But a state graph is used to determine the number of states and label them. It also allows us to determine the number of state variables and how we would label them. So basically, how many flip-flops do we need? We can then label the outputs and encode the outputs to states. When we're talking about encoding, that's where we have to do some number conversions, typically from base 10 to base 2. After we've created the state graph, we then create a state transition table using the state graph as a source. Then from the state transition table, we can write and simplify our design equations. So we can either use Boolean algebra or Carnot mapping to do that. Then we design our circuit. Okay, so what does a state graph look like? It's kind of intense, but a state graph shows the sequence of states that the state machine will transition to on each clock transition. So this is an example of a state graph with 4 states. Now I know this looks super intimidating, but we're actually going to break this into much smaller pieces and study each detail later. Right now, I just want you to focus on the parts and how they're related. So take a moment to analyze this and think about what you're seeing and how this could be representing how an input is controlling various outputs. So each bubble that you see here is labeled either S0, S1, S2, or S3. Okay, so these labels are arbitrary. They're just added on here, but starting at S0 is the most common way. Okay, so those bubbles are identified in green. We then also have those loops outside of the bubbles, and those are called transition arcs. Each transition arc is labeled with the values of the input variables that make the transition occur. So you can see we have S0, okay, and this transition arc is labeled right here with the inputs that make S0 occur. And then we also have that labeled over here so that we know what's going to trigger this to go from S0 to S1. And then we have the hold right here for the state. So let's take a closer look at these parts. First of all, we have the state bubble, which is right in the center, okay? And so let's break down the anatomy of the state machine. Okay, first of all, we have the state, which we already identified in the previous slide as labeled as S0, 1, 2, 3, etc. Okay, so the state graph shows the sequence of states that the state machine will transition to on each clock transition. So each state bubble is labeled, usually starting with S0, but again, they're arbitrary. And then we have each transition arc, which is labeled with the values of the input variables that make that transition occur. So for the input, x equals 1 to move to the next state in this instance. And then up here, as long as x equals 0, we stay in this current state. So that's what this little loop right here is indicating. State variables are the outputs of the flip-flops. So they're usually called QA, QB, QC, etc. So for these state variables, we have QA and QB identified in here. The number of state variables is determined by the number of states according to a function. And that function is that the number of states is less than or equal to 2 to the number of states variable as a power. So as an example, we have 2 states required, which would mean it's a 1 state variable. Okay. If we have 4 states that are required, then we have 2 state variables. If we have 8 states required, then we have 3 state variables, and 16 states required, it means 4 state variables. So why do we need to know this? Well, that's because many times we have states that actually go unused. So we may not have an output variable. It may just stay there. Also, the output variable is identified right here. So y equals 0 and z equals 1. Okay. Again, as I mentioned, that transition arc up here is a hold. And then we have that input variable, which is creating that hold. Okay, so as I previously mentioned, there may be times when states go unused. So an example of this would be that if a design needs 6 states, we need a total of 3 variables, because 6 is less than or equal to 3 to the third. But that actually equals 8 states, so we're only going to use 6 of them. Each state is assigned an output value for when the state machine is in that state. So right here, this is the output variable for when the state machine is in that state. So let's talk a little bit more about these state variables. The state variables are actually the outputs of the memory flip-flops. So for that reason, we're typically labeling them QA, QB, etc., because those are the outputs that are coming from the flip-flops. So as you can see here, QA and QB are identified inside of the state bubble. Okay, so here we have a 4-state example, which would require 2 flip-flops. So we have QA and QB, and they need to clock through 4 states, S0 to S3. So the first state, S0, QA and QB are 0, 0. All right, so that's indicated here, no lights. Second state, S1, QA and QB would be 0, 1. So QB would be lit, QA would stay not lit. The third state, okay, QA and QB is 1, 0. So this QA is lit, QB is not. And then in the fourth state, QA and QB are 1, 1. So both of them are illuminated. Okay, so now let's talk about what output variables are. So each state bubble is assigned output variables. So again, we're back to that the example that has 4 output variables based upon what state it's in. So what you can see here are the output variables. So you can see there's a key down here, and these are representing motor open, motor closed, gate open, and gate closed. So if we look here at S0, we can see that the outputs are MO equals 0. So motor open is a 0. Motor closed is a 0. Okay, gate open is a 0, but gate closed is a 1. As we transition to S1, the motor open becomes a 1, the motor closed becomes a 0, gate open is a 0, and gate closed is a 0. And then those outputs continue to transition just like that. Okay, we have the same thing for inputs as they transition. So basically, we would move from state 0 when we have the OS, so the switch is open, and then we don't care about the rest of them. But we would go from S0 to S1 if the switch was open. Then we come here and we would hold in this pattern, as long as we only had OL, which down here says open limit, is occurring. Nothing else matters. So as long as a limit switch is open, it's going to stay in S1. Then once that open limit switch is here and we get the various inputs, it transitions to the next state. So how do we go from a state graph, that really intense looking picture, to a state transition table? So we have to go from this very intense looking item to this relatively equally intense looking item. Now the good news is it's pretty much just plug and chug. Once you have the state graph done, the state transition table is just essentially filling in the blanks, as long as it's formatted correctly. So a state transition table is created from the state graph. So they describe the present state, or the inputs, okay, and the next state, the outputs that are associated with each state. So you'll see that we have, this is essentially a T-chart. On the left, we have present state and inputs, and then we have next state and the outputs. And then we have S0, S0, S1, S1, S2, S2, S3, S3, and over here on the outputs, S0, S1, S1, S2, S2, S3, S3, and S0. Okay, those are formatted that way because we have to start somewhere and then we have to transition to those phases. So this is how we format the transition table. We can then take from the state graph the different inputs and how they correlate to the outputs and fill that in. From there, we can then define our design equations using the outputs. So you need to notice that each state occupies 2 lines on the state transition table. That's because in this example, each transition is triggered by only one of 4 possible inputs at any time. Okay? So the input that causes the transition in S0, we have the OS and equals 0, or the OS equals 1. So because we have 2 instances that can cause it to transition, we have 2 lines in the table. So in a state machine, the next state is actually the output from the memory flip-flop. So QA, QB when the input is changed. So what we're seeing here in the transition table is that QA is equal to DA for the next state on one flip-flop, and QB is equal to DB for the next state on the other flip-flop. Okay, so that's what we're looking at. So for state transition tables, the outputs from the memory flip-flops are linked to the inputs of the combinational logic. That way a transition is made on the next clock signal to the next state. So what we're saying here is that QA equals DA for the next state on the flip-flop, and QB equals DB for the next flip-flop. Essentially what this is talking about is that when we are having that input logic, it's coming into here, and when we get the correct outputs sequenced from those flip-flops through coming out of QA, again, that's controlling it the same way we've controlled flip-flops the entire time. Just because they're in a state machine doesn't make them any different. Once we have QA and QB identified in the correct way, it's going to trigger it to the next flip-flop, which will eventually result in our outputs. So then how do we go about creating our design equations? Well, from the state transition table, you can now determine the unsimplified expressions for the input combinational logic and the output combinational logic. Okay, so in this instance, when you're looking at DA and DB, that's QA and QB. So DA is equal to QA, and that equals all of this. So remember, these are unsimplified, and that's because they're coming from over here. Okay, we have to identify the different states from the various outputs in order to get those. Okay, we also have to use our input logic to get our input sequences. So a little bit of a breakdown, but we'll break it piece by piece when we actually do this in class. Okay, so let's go ahead and look at a design example. So let's say that you have a design of a state machine that will count out the last 4 digits of a phone number only when an enable button is pressed. Okay, so that means there is an EN that we have to push, and that triggers the output of a 4-sequence phone number. So the output should hold the last number until the enable button is pressed again. So if the phone number example is 585-476-4691, the state machine is going to progress through 4691 when the enable button is pushed. When we push the enable button again, it will then cycle through 4, 6, 9, 1. So whenever the enable is a logic 1, the outputs will continuously cycle through the 4 values, 4, 6, 9, and 1. Whenever the enable logic is a 0, the outputs are going to hold at their current value. So if we hold the enable button down, it'll just continuously cycle 4, 6, 9, and 1. If we only pushed the enable button once, it would preview a 4. When we pushed it a second time, it would move to a 6. So for this design, any form of combinational logic can be used, but the sequential logic has to be limited to D flip-flops. So essentially we have our enable and our clock, and then we have C3, C2, C1, and C0. So we have to start by creating a state graph. So we have to identify the number of states that we need. So we have 4 digits in the phone number, 4, 6, 9, and 1. So we have S0 being 4, S1 is 6, S2 is 9, and S3 is 1. Now looking at S0, we are going to stay in S0 so long as our enable switch is equal to 0. It's just going to keep repeating. But as soon as our enable switch is equivalent to 1, we're going to transition to state 1. So that is a 6. We're then going to stay in state 1 as long as our enable is equivalent to 0. And as soon as it becomes 1 again, it will transition to numbered S2, which is the value 9. Okay, and that enable is equal to 0, and it will stay in S2 as long as it is 0 until enable becomes a logic signal of 1 again, which means we transition to state 3 or S3, where the value is 1. We are then going to hang out here as long as our enable button is equivalent to 0, but as soon as it becomes a 1, we will transition back to S0. So then we need to determine the number of state variables and assign them. So here we have QA and QB identified in each of the state bubbles, and we have 0, 0, 0, 1, 1, 0, and 1, 1. From there, we then need to encode our values. When we say encode the values, that just means that we're going to convert from base 10 to base 2. Because our largest output is a 9, we actually need 4 output variables in order to represent this, because 9 is equal to 1, 0, 0, 1 in binary. Okay, so our output variables are labeled C3, C2, C1, and C0. So if we look at state S0 up here, okay, the output 4 is encoded to binary, and that would be 0, 1, 0, 0. C3 is then 0, C2 is 1, C1 is 0, and C0 is 0. You can then see that we have encoded each of these other states across the 3 other state bubbles. So then we need to move on to the transition table. So looking at this transition table, you'll notice that each state has 2 lines on the transition table. One line is for when enable is equal to 0, which is our hold state, and one line is for when enable is equal to 1, which is our next state. Okay, so even though the enable switches in the first 2 lines are right here, we have the 2 lines, and then we have enable as a 0 and enable as a 1, the encoded output doesn't change until the clock signal transitions the circuit to the next state. Okay, so our encoded output does not change until the clock triggers it. Okay, so the encoded outputs for both of those lines of S0 are the same. Now you will designate the next state, QA and QB, on the output side of the table, but you do not change the encoded output. So if we look here, we know we have 0, 0 for QA, QB, okay, and our enable is 0. So QA and QB as our next input are 0, 0, DADB 0, 0, and then we have 0, 1, 0, 0, which is our 4 binary. Once we have QA and QB and our enable triggered, QA is a 0, QB is a 1, we have 0, 1, 0, 1, 0, 0. Now, essentially what's happening right here at this moment is the clock signal is triggering. Once that clock signal is triggered, we can essentially move all the way to the left and begin that process again with our hold state and then our next state. So then, after we have created our transition table, we're going to work through to create the circuit for our design. So we're going to have looked at our design equations, we're going to have simplified them as best we can, and then we are going to create our circuit such as this. So we have our inputs, We have our combinational logic, our memory, and then our combinational logic on the back end, which we'll take a look at how that matches the block diagram in just a second. But in the meantime, let's take a look at DB. Is there a better way to implement this besides 2 AND gates and an OR gate? Take a second to think about it, and then I'll show you what I'm talking about in a moment. So if I look at what I have right here for my logic, I then have a couple of places where I can simplify a little bit. That's actually going to result in the ability for us to use an XOR gate right here, okay? So because we're able to use an XOR gate right here, that limits the amount of gates that we're using. Now, you do not have to use an XOR gate. You don't have to simplify that far. Just remember that in real life, every gate we have causes a little bit of a time delay. So less gates is cheaper and a little bit faster within the circuit. So let's take a look at how the block diagram actually lines up to the schematic. So here we have our inputs. Input is going right here, so that is our enable. Our input combinational logic starts at the inverter and essentially ends right here at the outputs of the XOR gate in this last OR gate. It then transitions into the memory flip-flops, which are right here. So we have DA, DB, and then QA, QB. Okay, and then our clock signal is controlling both the clocks there. You can see the presets and clear are both set to power. And then we have our outputs, which are right here. So we go to the combinational logic that is on the output right here. And then our final outputs are the probes. So C3, C2, C1, C0, and QA and QB.